So hi everyone, I'm Shani Finikak from the University of Johannesburg. I'm a PhD student there, and I will be presenting a symmetry-based model Hamiltonian for topological analysis. Next slide, please. Cool. So what we're having a look at is how to model a physical system. So generally, when you want to model a physical system or describe the Hamiltonian of that system, you are kind of stuck playing between two different things, depending on what you want to do. So either you want a really nice and analyzable simple model, or you want to go for a model which is quite complex, but very accurate. So depending on what you want to do with your system, you may or may not want it to be very accurate. So for example, if you need to represent your system completely, you would aim for accuracy. Whereas sometimes what happens is you need to be able to analyze the properties of your system very easily. So for example, we have a look at a class of materials called topological insulators. Topological insulators, as you can see on the diagram on the right-hand side over there, are insulating in the bulk, but conducting on the surface. Now, for these specific models, you are only interested in the two bands close to the Fermi level. And if these two bands have a gap closing or move from obviously being insulating, so an open gap, to conducting a closed gap on the surface, then you can say that this material is a topological insulator. Now, you can define these properties with different things called winding numbers, or material properties called winding numbers. And using these winding numbers, you can then describe your system. Now, in order to calculate these winding numbers, we need a very, very analyzable model, but we also needed to at least represent our material to a certain extent. Next slide, please. So oh, sorry, this is looking really bad. It's not showing properly. Is there a way you can share the PDF instead? Or can I share my screen?
Shani, you can try and share now.
Shani, you can share your screen.
So sorry, I'm just quickly going to share my screen. Cool. So hopefully you can see that now. It's just taking a minute to share. Sorry about that.
Okay.
So that's a little bit better. All right. So as I said, let's quickly have a look at the general approaches in the field. So generally, of course, people are more interested in the accuracy of their system. So they go for very, very complex models. What you would do for a complex model is you would need to first choose your material, identify all of the different components of the material, whether those are the specific atoms of the material, the orbitals, things like that, maybe even the Wannier centers of your material. Then using these details, you would set up the model itself, and then you would use the model to fit some form of data such as DFT. Now, unfortunately, this is a very involved process. So what you would need to do to set up this kind of model, here's an example of where they set up a fully detailed tight binding model in the reference shown on the bottom of the slide. So what they had to do here first was they first had to calculate, so they picked a very, very specific material. And then using this specific material, they calculated where the Wannier centers of the material were. And then after that, they could set up a tight binding model by running through a whole bunch of iterations. And then they could symmetrize it and evaluate the model. Now, this model ended up fitting very, very well. So it fitted the DFT data extremely, extremely well and represented everything to the extent of a whole bunch of bands above and below the Fermi level, and the chemical bonding properties and all of these sorts of things. Now, before I move on to what we would do in our approach, I just want to point out that, again, for topological insulators, we are only interested in the two bands close to the Fermi level. So we're only interested in those two, and we only want to represent them close to where the gap closing would occur. In general, for us, this would occur around the gamma point. So we will focus on fits, or we would focus on models that could fit that really well. All right, so our approach now is to first set up a general basis, and then based on some kind of property, such as the symmetry, we would like to class a whole set of materials together. So in the general approach, so these approaches over here, you would have to select a very specific material and then look at all the properties of those. We would like to instead just find a general way to represent a whole class of materials. So for example, we might like to represent all of the C2 or D4, C2, D4, C2, anything like that, symmetry groups. From this, we would then like to derive a very nice analytic model. So, as we said, for topological insulators, we would really like something very easily analyzable. So because we want to represent a very general system, we, for example, started with something very, very easy. So over here, we have a 4-atom basis. And based on that basis, we are looking at next nearest neighbor interactions. Nearest neighbor interactions first. And then we can set up a very simple SSH model. Now, using this model, which is shown down there in the bottom screen, we can calculate the topological invariance over the parameter space. So you'll see in the middle, we've got a Z equal to 0, 0. So this would indicate a trivial phase, so just an insulating system. And then you could, for example, get the orange and green squares, which would indicate edge state conduction, and the red corners, which would indicate corner state conduction. Now, this model is very, very simple, so we're not sure that this can quite represent a real system. So what we might want to do is move slightly away from making it very easy to analyze, maybe make it a little bit more complex, but still analyzable. So we have to give sometimes to get, right? So now in this case, we would include next nearest neighbor interactions. So you'll see over here, instead of only having terms off the diagonal, so off the main diagonal and the off diagonal, we now include next nearest neighbor interactions. So we make our model a little bit more complicated. Using this model, while we do follow a slightly different approach, we can still scan the parameter space and split the parameter space into bulk, edge, and corner states. So again, yes, we have made our model more complicated, so we have to use a slightly different method, but we can get to roughly the same results. So this should still be okay. Now, as we said, the important part of this is to check if it can fit this general class of physical systems. So here we have a set of physical systems from the same symmetry class, and we check if they can fit. So if we start with If we start with the material on the left-hand side, we can see that it fits relatively well close to the gamma point, whereas the material on the right does not represent the data well at all. So unfortunately, we've decided that our system over here is a little too simple. So now we look at a slightly different approach. We can actually set up a 4x4 Hamiltonian or any general 4x4 Hamiltonian using a set of matrices. So in this case, for 4x4 matrices, you can use something called a Dirac matrix. Now, a Dirac matrix is just an extension of the Pauli matrices in 2D to a basis set in 4D. So we can set up this general Hamiltonian, and based on the way that these different matrices react to the symmetry operations in our symmetry class, we can build up these terms listed below. Now, the details of these are not super important. The only important thing here is we can see that in this case, we've now gone from something with quite a simple number of parameters to something with way more parameters. In fact, in this model, moving from our previous model, which had 8 parameters, we now have 20 parameters if we only consider this model up to cubic order. This model is infinite, so unfortunately, we do have to cut it off somewhere. Now, let's again check if this is actually going to fit our data. We see here that we do fit our data really well. So here we're just looking at our first material again. We see that both our models represent this data, but the second one with the 20 parameters represents this a lot better. Now, of course, you can fit anything really well with 20 parameters. So as expected, the second material fits really well around gamma as well. Now, having this many parameters is quite difficult to work with, and we believe that this can more or less fit anything. So let's quickly just have a look at what we've done here. So we've gone from this really, really simple model, or slightly more complicated simple model that's really analyzable, and we've extended it to something with 20 parameters. Now, unfortunately, that means that we're in the same situation as the general approach. So we've gotten to something which is, again, not very analyzable. So what we want to focus on in this work, and this is the main goal of our project, we haven't quite gotten there yet, it's our work in progress, is we want to find a model that is going to sit somewhere between these two things. So something that is very analyzable, but also rather accurate. So hopefully, by the end of our project, we find something that hits that sweet spot in the middle, where while our model is analyzable, it at least also represents our data. And hopefully by doing this, we can describe our general set of materials. So these general 2D topological insulators.
You have a minute there, Chani.
Oh, I'm done. Thank you. I would just like to thank, yes, the NRF and obviously the Center of Excellence in Strong Materials because they funded me. Thank you.